Area of parallelograms and triangles, section 10.1. How do you like that? All right, we've got a lesson objective, a learning target for today of to find the area of parallelograms and triangles. All right, for most this is a review, area of parallelograms and triangles. However, it is the start of this unit, which is all about area. We're going to cover in this unit areas of different shapes, and we're going to also look at relationships between areas of similar figures and a few other things that have to do with area. So we're going to extend your knowledge of area a little bit in this unit. I'd like to start off with just a 3 theorems that hopefully you know. If you don't, make sure you have these ingrained in you now. So, theorem 10.1 says that it's the area of a rectangle. The area of a rectangle is the product of its base and its height. Very simply put, base times height, or length times width. That may be the way that you learned it. 10.2 says the area of a parallelogram. Same thing. The area of a parallelogram is the product of the base and the corresponding height. So the one thing about a parallelogram is you may always have this base height or this base distance, but you may not always have the height. Sometimes you may just have a side length here, but what you really need is the height of it. So a perpendicular line to the base that goes up to the other side is perpendicular to both. Okay. And then in theorem 10.3 is the area of a triangle, very similar to that of a rectangle, only you are multiplying it by 1/2 or dividing it by 2. So the area of a triangle is half the product of the base and the corresponding height. Okay? If you look at a triangle like this would be the base, yes, and we'd have to find the height. If you have a right triangle, we always know that the base, like the two legs would be the base and the height. And this one kind of looks like a right triangle, but it doesn't have the right triangle symbol. So if we want to fill in the blanks here, so looking down here, a base of a parallelogram, so if we're talking about the base of a parallelogram, can be any one of its sides, but then the corresponding altitude, we've learned altitude before, is a segment perpendicular to the line containing that base, drawn from the opposite of the base. And the altitude, so the height is the length of this altitude. I kind of described that before. The height, though, is the length of that altitude. And the unit for area is always squared, or square units. Okay? Keep that in mind. You always square area, or the units for area. So, a couple of examples here. Looking at the first two. Letter A, we have 3 different things given to us. What's the area of a parallelogram? Remember, area of a parallelogram is just the base times the height. So we have 24. So area equals 24. That's going to be our base. Times the height, which is actually 6. 8. The 8 has nothing to do with this really right now. The 24 times 6 is what we're looking for. And that would end up getting 100... 120, 144. And we have centimeters squared as our units. All right, this one we have another parallelogram. It looks like we can use the top base here. That's okay. Either one of these would be bases, but since we have this as the height, right here, the altitude, we're going to use the 1.4 because this would also be the same as 1.4. So we're going to say the area for this parallelogram is 1.4 times the height of 2.3. Okay, and 1.4 times 2.3 I don't know by heart, so we're going to pull out our calculator and do 1.4 times 2.3 and get 3.22 inches squared. Alright, number C, letter C, what is the length of the missing base? So here's an application where you may already have the area. So in this case we have area equals base times height. This time we have the area, which is 28 meters cubed. And the height is 4 meters, so we need B times the 4. Alright, now, very simply, we can solve this one-step equation for b, and by dividing 4 on both sides, and we get b is equal to 7. Now think about this problem. It's asking for the base length. So it wouldn't be, in this case, meters squared, because it's not asking for the area, it's just 7 meters. Alright, this is a little bit more tricky of one. Problem 2, we have here finding a missing dimension. We are given quite a bit here. And we're trying to find, so it says find the area of the parallelogram in A, B, C, D, 1, and then use the answer to number 1 to find the missing height. Okay, that would be the DE there. So what I'm going to do is I'm going to utilize the base as this length right here. So area is going to be equal to 13. Now the height has to be perpendicular to that in altitude. We actually do have a perpendicular altitude right here. It's not the 9.4 because that's not the length of the height. The perpendicular altitude would be the height of 9. Alright, so 13 times 9, and we get the area, which is 117. So 117 inches squared. Now, we can use that and this as the base to find the height. So we can plug that in. We can say 117, because that's the area, is equal to the base of 9.4 times the height that we're missing that goes along with that. And we know that's perpendicular. We know that's the height because it goes from one base to the other, and it's perpendicular, so it's an altitude. So we divide both sides by 9.4, we can get that missing height. 117, oops, divided by 9.4. We're going to round it. We're going to say that 12.4. So h is equal to 12.4. And now again, that's not inches squared. That's just inches because we're just finding a length here. So I should take that, use what we just learned, and try that on this one. We want to find h. All right. Given what we have, you're going to have to find the area first and then find that missing height. So go ahead and pause it, and then you can unpause it when you're done, and I will show you the answer. All right, feel free to take a look at my work. In the green, I found the area using the base of 8.4 and the height of 5 then. And then I used that and the base of 6 to find the height. And it equaled 7. All right, moving on. A little bit more about triangles now. So you can rotate a triangle about the midpoint of a side to form a parallelogram. So if we wrote the midpoint here and we just rotated it like was done here, it would make the same triangle just rotated would form one whole parallelogram. The area of a triangle is half of the parallelogram. That's why it's 1/2 times base times height. So let's use that, and now let's find the area of the triangle. You just have to know what the base is and what the height is. So remember, height is only determined by an altitude. Same thing as in a parallelogram. So in this case, for letter A, we have the base. I'm going to use this as the base is 5 times 5, and then the height would be the perpendicular one would be 12. And in this case, 1/2 times 5 times 12 would be equal to half of 60, which is 30 meters squared. Now the one on the right is a little bit different because we don't have a right angle in the triangle. It's not a right triangle. We can choose this as the base. So we do area equals 1/2 times 12. Now the height would still be perpendicular to that going to the other end, and that would be this altitude with a height of 10. So multiply with that by 10. So our area would be half of 12 times 10, which would be 120. So we had 60 in this case, centimeters squared. Okay. Now here's a couple of unique ones where we have multiple things going on. So for problem A, we're going to find the area of the irregular figure. So to do that, we want to find the area of each shape. So we want to break it up. Right now, if we can do triangles and parallelograms or rectangles, that would be ideal, and yes, we can. So if we look at here, that on the left is a cube, and then here is our triangle. So the area of the triangle is 1/2 times 8 times 15. And the area of the cube is 15 times 15. And if we add those up, we get the area of the whole figure. So 15 times 15 is, I believe it's 225. And this would be 60, I believe. I'm sorry. I added an extra little thing there. 60 centimeters squared. Now, since those are our two smaller parts, we add them all together. The area of the whole thing equals 60 plus 225, which is equal to 285 centimeters squared. So that is the entire shape. So take a look at this one in letter B. Why don't you try this one on your own? Again, pause it, and you can unpause it when you got it, and take a look and compare the answers. All right, so feel free to take a look at letter B for this. The two parts, we got 40 or 20 meters squared and 40 meters squared, adding up to get to 60 meters squared total. So the last part of what we're going to do today is going to deal with some coordinate grids. So it says find the area using coordinate grids. Now, sometimes when you're finding the area using coordinate grids, it'll be really easy because all the lines are horizontal and vertical, and you can actually count them. Sometimes they won't be so easy. You may have to use the distance formula. So let's check this one. We have A is -3 and 1. B is -3, 4. C is 7, 1. 1, 2, 3, 4, 5, 6. Oh, it's not even on there. 7, 1. And D is 7, 4. All right, this one's going to work out nicely. This is a straight rectangle. And we can count. This is 3. This is 3, 4, 5, 6, 7, 8, 9, 10. It would be 10. So the area of this one is just 10 times 3, which is 30 units squared. Interestingly enough, if you count all the squares inside of this, it would also be 30. So that's another way to double check the area. Letter B, we have -1, 1, -1, 6, and 2, 6. So not quite as easy because it's a triangle, but it does still go along the horizontal and vertical. So we have a 3 by 1, 2, 3, 4, 5. So area, we still have a base of, we have to do times 1/2, and then a base of 3 times the height of 5. And 1/2, 3 times 5 would be 7.5 units squared. All right, last one is problem 6. We have these vertices, -4, 3, -3, 2, -3, 4, -6, and -2, -6. So what I first want to do with this is to graph it. Let's take a look at this and graph those points. So -4, -3. 1, 2, 3, 4. 1, 2, 3. 2 and -3. 1, 2, 1, 2, 3. 4, -6. And then -2 and -6. So we want to determine whether it's a quadrilateral, is a square, rectangle, or parallelogram. So it's definitely not a square or rectangle because we can clearly see that the sides are not forming 90-degree angles. The slopes of those are not perpendicular. They're not opposite reciprocal. But there are parallel sides, opposite sides. So this is a parallelogram. Now we want to find the perimeter of quadrilateral ABCD, and then find the area of it. The perimeter is going to be a little bit more challenging than the area. Because we can see 1, 2, 3, 4, 5. Each of these sides is 6. But we don't know the lengths of these diagonal sides. So to do that, and they are going to be the same since the parallelogram, we just have to find one of them. And to do that, we're going to have to use that distance formula. So let's find the distance between, let's do these two. 2 and negative 3, so that would be B. And 4 and negative 6, so that would be C. All right, A, B, C, D. I'm going to actually label these with black. So that's 6 and that's 6. All right, so distance formula, if you recall, is the square root of x2 minus x1 squared plus y2 minus y1 squared, all under that square root there. So if we're going to plug in this in, x2 minus x1, if we're doing b to c, it would be 4 minus 2. We got all kinds of things going on here. All right, plus y2 minus y1, so negative 6 minus negative 3, or plus 3, squared, and all that's the square root. So we have the square root of 2 squared plus negative 3 squared, which is the square root of 4 plus 9, which is the square root of 13. It's not going to be a perfect number. However, we can do 13 and square root, well, 3.6, we'll say. We'll label that as 3.6, and this is 3.6 as well. Those are just those diagonal sides. So to find the perimeter, we're going to do 6 plus 3.6 plus 3.6 and get a total perimeter of 19.2. That is just units because that is just perimeter. Now this is really focusing on area. So to find the area of the parallelogram, we still do base times height. And in this case, we have the base of 6, and we can count the height. The perpendicular height would be 3. Whoa, my mistake. And so that would be times 3, which is 18 units squared. That's interesting that the area and the perimeter are very similar in this one. That's not going to always be the case, though. So, closing questions, you can take a look at this and see if you can figure out the error analysis problem. Focus on the question, how do you find the area of a parallelogram and the area of a triangle? What does each variable in that formula represent? That takes us back to our objective of finding area of parallelograms and triangles. I know we took it a little bit farther with finding missing parts and doing the on a coordinate grid, so it took a little bit longer than usual. However, we're in geometry, so we got to take it a little bit farther than what we knew already. So I hope you learned something here on the area of parallelograms and triangles. This is the first section of Chapter 10. We'll see you later.